Hello, good evening, good morning to all our attendees today for this second in our series of fiber optic sensing webinars. Thank you for joining this morning, and we will have taking questions at the end of this at the end of the webinar. So there is a place where you can type in your questions. So please, as you think up some questions, please go ahead and type them in, and we'll try to get through all the questions at the end. Today, as I said, is the second of our series of webinars. This is we hope to do some more through the coming year. We're also we're open to suggestions about information and topics that people are interested in around this subject. Today's subject is really geared towards understanding how fiber sensing, distributed fiber sensing, can complement and contrast with wireline point sensors that we're all more familiar with, I would say. So without much ado, again, thank you for joining. And Mike Webster is our presenter today, and he will take us through. As I said, if you have any questions, please do go ahead, write them in the box that's available, and we will get to them at the end. We're hoping to complete this webinar within the hour. The actual talk should be around 40 minutes with about 20 minutes worth of questions. So again, thank you for attending, and Mike, please.
Right, well, thank you very much, Marvin. And this is a rerun of something we did last week on fiber versus wireline. The first talk that we had, it was just an introduction in terms of here are the different components and things we need to think about when we want to perform a fiber service. On this occasion, what I wanted to focus in on, because most people tend to be very familiar with wireline, I wanted to tease out some of the differences and pros and cons of using wireline versus fiber, and what that means to us. So without further ado, this is the same slide as we had in the very first presentation, just a little bit about my background, who I am and what I've done. To get into the meat, what we want to do is to run through distributed fiber surveys. Why do we need to run a distributed fiber survey? What advantages fiber brings to the table? Am I simply just adding cost? People see many forms of surveillance as just simply adding cost, and if they can get away without doing it, then they won't. It's always frustrating when it's the first thing to go during times of austerity. They tend to cut back on surveillance as being an easy target. We've got perfectly good wireline measurements, so why would we need to change to this new form of measurement? So what are the motivations there? Wireline's mature and it's well understood. So what's driving us to this new type of measurement? And I think at the end of this, what we'll end up with is the advantages to running both services. It's fair to say that fiber brings something extra to the table that is not available or not easily available with wireline. And if we combine the two, the combination of those things actually brings a heck of a lot more value to the table than the cost that adding a fiber service incurs. But essentially, it's all about surveillance. So the surveillance, the activity is gathering information. So really, we're trying to gather as much information about the well or the reservoir as possible. And we need to use that to influence, manage, or direct something that goes on either in the reservoir or in the well. The value comes from the use of the information. And I probably don't have that much of a preference as to whether I gather that with wireline or with a fiber distributed measurement, as long as I get the information to make a decision. However, fiber does bring something new, and we'll see some examples of that in this particular slide pack, and hopefully I'll guide you, lead you through as to why I'm so keen about running fiber services and why surveillance benefits as a whole, and not so we're not throwing away what we did before, we're supplementing. So we know wireline. It's been around for as long as I can remember. We've got E-line or slickline services. Those are almost ubiquitous. Anywhere in the world there'll be a rig capability to run either electric line or slickline services. So it's very mature technology, wide variety of measurements, wide number of service providers that can give us a perfectly good service. And you only have to look, I mean, the photograph there is just a small selection of the multiple spinners that are on the market, all of which have been designed for different purposes and have different sweet spots in terms of their operation. And we've got the ability to combine services and using different physics to give us a more unique diagnostic of the well problem. So everybody's used to taking a range of sensors and combining those onto a production logging tool string to satisfy a particular need within the well. We've seen many different phase type measurements developed over the years, and there's pros and cons as to why you would select each. And most people are aware of what mix is best in each circumstance. So we know wireline. They are providing us with a specific value at a point in the well. And when we run a survey, we generate a locus of those points as we pull the sensor package up through the well. If a well's behavior is unstable, that's not going to form a great basis for interpreting the results. So my preference is to be very proactive in our surveillance. And so what we need to do is to try and gather as much information as possible in a timely fashion before we start to run into stability issues with the well, because it just adds a whole layer of complexity onto things that just causes us grief. Historically, many of the case tool logs we've run, we've gathered a base log and then used that to compare successive monitor logs. I remember when I started in the industry, it was very common to run a base log early in a well's life and then use that as a reference point as the well matures, and try and play off the differences between the initial baseline and a successive monitor log to tease out more information than I would do if I only had simply the monitor log itself. We've tended as an industry to move away from that as the norm. It's seen as a cost, so why bother gathering a base log? It's just a luxury. If I can get away without gathering a base log and wait until I've got a problem in my well, then that tends to be how we operate. It's a very hand-to-mouth existence that we tend to have moved towards in surveillance these days, which is something that I'm quite uncomfortable with, and do prefer the baseline monitor log type practices that we've had in the past. So the principle here is that we're looking for very small changes over a period of time from a reference baseline. We've seen many of these children's books where you play spot the difference. There may be a cartoon that you flick from page to page, and you can pick up very, very small differences that otherwise you wouldn't notice if you were looking at things individually or on the same sheet of paper. And that principle is something that we want to think about when we run a distributed survey. So what do we know Wireline, and this is an example of GOWell's alpha noise log. And we've got on the far right-hand track, there's a leak in the casing, and we can see where that leak occurs. We've got some acoustic energy that's creating a signal for us to measure over quite a broad range of frequencies. And in this example, we'd be quite happy to say, yep, that's where my leak is at 2657 meters, and call that a good measurement. However, if that measurement were periodic, so if it only occurred every 5 minutes or 10 minutes, if there was an accumulation of pressure and then a release of energy to create the signal that I'm measuring, if the tool was not within the range of that leak when it sets off, then I may not pick it up. So noise occurs at a specific depth. If I know where to look, I'll pick it up as long as it's active when the tool passes the source of that noise. The tool temperature, the two temperature profiles, they give me a snapshot at a specific time period. And so this is a shut-in pass and a bleed-off pass where I've run a log over the entire interval, and I'm picking up difference in temperature between the shut-in and the bleed-off. But those are just two snapshots, and I don't know if there's a general increase or decreasing trend, or how quickly that occurred, or any details. It's just purely a snapshot. But this is the information that we've come to use historically, where I'm running a package of instruments. I get a locus of points for my log, or maybe I've got point occurrences of specific events. So technology does continually to change, and we always want to improve what we're doing. So we are trying to make more efficient use of our well stock and our reservoirs, and to make better decisions. And for that, we need the availability of data to make those decisions. If new technology offers us an alternative, then we should look at it and examine it on its merits. So the statement at the bottom there, grandmother's wisdom: if you always do what you've always done, you'll always get what you always got. And the image, the same old thinking, same old results, conveys the same sort of sentiments. And so the ability to pull in something new and use that to try and help create more value from a specific situation is what we're trying to achieve. So the new technology is a distributed measurement run on fiber. So we get the data over the entire length of the well all the time. I don't need to make any choice on where to survey. As long as I can deploy that fiber to the bottom of the well, I'll get everything over the entire length of that well, the whole time I'm pulsing down that piece of fiber. And it's the ultimate in time lapse. So I've got the ability to look at the profiles at the start and over the entire duration of that survey interval. So I've got a limited number of measurements here. The common ones commonly available on the market are temperature and acoustics. So while with a production log, I can have many, many different physics to try and help resolve the situation. You only need to look at the proliferation of the different types of phase measuring devices and bubble counters and all these instruments to show that there's a huge array of physics I can employ to try and resolve rate and phase from a well. With this measurement, with a distributed measurement, I've only got two, temperature and acoustics. There are others coming on the market, but those are the two common ones at present. But temperature and acoustics are particularly useful to me, especially for well diagnostics. And I've always been a fan of a temperature measurement anyway, even on a basic production logging tool string. It's always proven to be a really valuable piece of information. So now I've got this all the time over the whole well. So what possibilities does that open up to us? And it boils down to, I can make changes in a well while I'm in that well and look at its reaction over its entire length. And that brings out something that we couldn't normally do with a point measurement, where I may be able to pick up within this vicinity of the tool what's going on. But if there are dynamic changes going on out with that sensitive area, then I'm simply not going to see them. So this is the key useful piece of information I get from distributed fiber. It's the ability to induce a change when I want to make that change in a well and observe what happens downhole on the fiber. And it is the ultimate in time lapse. And the way that these surveys, distributed surveys, generally play out, you would end up taking a baseline survey as soon as you go into the well that may last an hour or two, just to establish what normal looks like. And then you would start manipulating conditions at the surface of the well to try and induce some sort of change and create some sort of fluid movement or something in the well itself. Now that could be a combination of either bleeding off tubing or annuli pressures, or injecting into the annulus, or any combination of those to try and get things moving, to get some sort of dynamics going within the well and pick those up on temperature and acoustics. And that, to me, is the key application for a distributed measurement. So let's have a look at some examples. So an example of action and reaction. In this particular case, we've got a well where the baseline temperature is shown on the left, and we induce a change in the annulus and observe what happens further on in the trace. So time is increasing from left to right, and I've got depth on the y-axis, and we've created this difference plot where if I look at the baseline to the far left, I'm looking at successive traces with respect to that baseline and looking at the delta T, the difference in temperature from that starting point. And it becomes really clear that there is activity in this well that happens towards the base and is causing a slight heating from the baseline. And then further up the well, we've got the progression of some cooling effects that transfer up the length of the well itself. So straight away, I've taken an action in that well, and I've made this observed reaction, and I can start working with that and interpreting it. Here's another one. And this is of dynamic behavior, where when we've injected cold water into the well, and again, we've got to the left-hand side of each track is the baseline, and then when we start injecting cold water, we get a specific point where on the temperature track on the right, the blue starts to appear and then fall down the well, and so we can identify a leak point at that location. It's fair to say that in most fibre surveys, while there is a reason why we go into that well to make a measurement, almost always or very frequently we find something else about the well that we didn't know about. And in this case, there are clearly activities going on deeper in the well that the operator wasn't aware of. And that comes out in both the temperature and the acoustics. So if you look at the DAS survey on the left-hand track with annulus injection, we can clearly see about halfway down the well there are activities going on that originate from when we started annulus injection and movement of coherent energy down that well. So there is something going on much deeper that needs to be investigated. And it's nice to see there is a correlation between the acoustics and the temperature, where we've taken some action in the well, created this dynamic situation, and made an observation on both the acoustics and the temperature at the same time. Now, the interpretation in terms of, so what does this mean? I need to pull in additional information to make sense of this. I mean, these are just two measurements, and so this is where I need to start pulling in the casing information, cement information, the overburden and the porous and permeable beds that are in the overburden, the completion. There's many things that need to be brought to bear to try and come up with a solution as to why the well is reacting the way it does. Another example of dynamic behavior, so we've got a chemical injection system towards the bottom of the well, and I can see that there is activity on the temperature profile. It's very subtle in the plain temperature display. So if you just look at absolute temperature on the left, I'm not really picking out too much detail. I can see there is something going on. Second from the left is a difference plot where we're looking at the difference from the reference, and straight away I can see, yes, at the chemical injection point there is a distinct change, and it traverses down towards the base of the well. And there are other ways of displaying the data in the other two tracks to the far right and second from right. These are successive differences between traces, and then the far right is the difference in the slope or rate of change of temperature with depth. And again, both of those show features that are related to the chemical injection at the bottom of the well. But we also see at packer depth there's activity as well. So clearly in this particular well, not only is there an issue around chemical injection, but clearly there's something going on at the packer as well. A time lapse. In this case, we've got absolute temperature on the left, and it shows some features at the mud line. So if I look at the blue interval on the left, that's the North Sea, and I've got a seabed moving down into the overburden, and I can see there is something going on midway through the survey. But when I start looking at and using the time-lapse ability of the distributed measurement, I can really tease out what's going on in this well. So again, we've got about an hour or so's baseline, a couple of hours baseline, where nothing much happens. And then as soon as I start to induce a change in that well, on the left, the right-hand side, where I'm looking at the relative difference from that baseline, all of a sudden I can see a really strong signal of heating and cooling within different portions of the well. And that's a really good example of the ultimate in time lapse, because I may be getting these traces on temperature every minute, 3 minutes, 5 minutes, however it's set up. But if I take the baseline and then start using that baseline and the difference plot to try and tease out quite small, subtle differences within the data, then it makes life a heck of a lot easier when it comes to identifying well issues. This example is kind of interesting because quite often baselines are not true baselines. So in this case, towards the bottom of the surveyed interval, we've got a couple of features that are progressing down the length of the well, down to the bottom of the well. Many reservoirs are depleted now, and in a mature field, it's perfectly possible if you had a porous and permeable interval in the overburden for it to be at a higher pressure than the producing interval itself. And in this case, we've got some intermittent events that are progressing down the well with approximately a 40-minute separation between them. And again, this is a feature that we can see quite often in distributed data, where you get a net accumulation of energy in a part of the well, and it overcomes a particular threshold, and there's a release of energy, and it dissipates, and then it builds up again. And in this case, it's a 40-minute periodicity for this particular effect to occur. All we can say in this case is that at some point shallower than where we've picked up the initial feature, there is a source, and that it's progressing down the well. If I didn't have distributed data, if I had conventional log data, I wouldn't be able to pick up these events unless I was adjacent to them when they occurred. So a really good example of, I've done nothing to the well is clearly not static, there is activity in the well, and I'm picking it up in the fibre. Again, this would point to going back to the well and taking longer at recording a baseline to identify exactly which the source of the energy is, and looking at the frequency of occurrence of that those pulses as they occur. Again, another example where we've got an initial baseline, and in this case, it's again not static. So direction and velocity. Here we're getting clear indications of upward movement of energy at about 0.2 meters per second, about 0.7 foot a second, from the bottom of the well, from the below the survey interval, right the way up over the length of this survey interval. And that's something that, while we might detect some sort of activity on a conventional log, this is a clear indication of direction and velocity over the period of the survey in this particular case. And then transients. So the ability to make a change in a well and observe that change having effect on the well, and observe the decay away of that over a period of time before inducing another change. So here we've pressurized up a volume and caused this temperature signal, and we've held that pressure, waited for that to decay away, and then stepped up the pressure again to create another signal later on in the survey. And again, this is using the fibre data almost in real time to allow us to see transients as they occur and understand and know when they get below the detectable limit before I then take the next action in the well. And again, that's quite hard to do with a distributed survey, with a wireline survey. If I had a wireline tool sat at the very bottom of this well, I'm going to see nothing. There's no change over the duration of that whole sequence of events. But clearly with the distributed data, not only am I picking up the changes, but I'm also observing the transients and then doing something about that and taking a subsequent action afterwards. It's a complement to wireline. So in this case, there is a huge amount of value to be gained in using fiber to make a survey of the entire well to allow you to then decide where you want to target a very specific wireline calibrated measurement. And in this case, we've got some activity quite shallow in the well. If you look at the middle figure, there's a little blue area indicating that there's something going on at that particular depth. And that allowed the targeting of that particular interval, quite a compact interval, with a specific noise log on wireline to try and tease out the detail. In this case, it identified 3 specific tubing leaks at 3 specific points. And that, to me, is a really powerful way of using distributed measurements, is combining that with stuff that we know and love and extracting a lot more value out of it. And all of those examples have been quite qualitative. So we're simply looking at an image and then making some sort of visual interpretation of that image and taking a decision on that. But fiber distributed measurements can be quite quantitative as well. And this is an example where we're using the temperature in the distributed fiber through an application. This particular example is from ISP's Plato application, where if we already have the properties of the fluids involved, then we can translate those thermal changes into rates. And in this case, they've got a calculated rate of 4,000 meters cubed per day, which matches the surface rates that they've recorded in the well. And we've got from the distributed data a good idea of which intervals are contributing to that flow. So if we wanted to get quantitative with it, then there is applications out there that will help turn the visual information, the subjective information, into much more quantitative information. I do need to have extra knowledge about the fluids and the situation to help do that, but that's perfectly doable. So the applications of distributed fiber. So the characteristics of fiber surveillance do make it ideal for flow assurance, well integrity and leak detection applications. The ability to make a change at the surface and immediately see the effects of that change, that plays absolutely into the strengths of a distributed fiber measurement. The fiber technology and processing is rapidly improving, and these things will get better with time. But already over the course of the last few years, we've seen this become a bigger and bigger and ever increasing part of our industry. And it is something that people need to get comfortable with the technology and understand the strengths and limitations of the technology to squeeze the most out of it. A lot of the improvements are related to the surface interrogation units. And the great thing about fibre, if it's permanent fibre, the fibre itself is fairly inert. It's the surface interrogation unit that really creates the data stream that we're using. And as those increase or improve, then we will get better and better quality measurements. There is an increasing choice in the market now, with a wider range of applications and budgets. So this doesn't have to be a permanently installed thing. We can go with quite modest fiber deployment techniques, either with monoconductor, slickline, or the fiber optic darts, and those are increasingly available. And in terms of the actual acquisition units, the interrogation units, those are becoming smaller and more portable and more ruggedized, and can be shipped out to more hostile environments. So what I want to leave you with here is that fiber is a complementary service and not a replacement. It's fair to say that the most efficient way of using fiber would be to use it as a pre-survey, so that I can then target my wireline sensors and measurements in a much more detailed way. So it's another thing to add to the toolbox. It is absolutely not a replacement for conventional. The objective here is to try and be more efficient and effective at diagnosing well problems. And so adding this piece of information really does bring something new to the table. So I kind of want to start wrapping up now. I've been going for just shy of 40 minutes. But just to say that GOWell certainly intend to have some training in different aspects of fiber and the equipment, and Marvin will let you know when those are occurring. And they are a global company, and those are their global locations. And so if you're interested in learning more about fiber and GOWell's activities within that arena, then contact your local GOWell sales person, and I'm sure they'll be able to help. And if they can't help, I'm sure they'll be pinging an email off to myself or Marvin to try and get you the answers that you need. So with that, I'd like to open it up to any questions. Marvin, if you can be the master of ceremonies and direct them as required.
Okay, thanks, Mike. That was great. So yeah, if anyone has any questions, there's a little box there. You can drop us a note. Don't see any questions yet, but
I think we did have we did have a question that came in actually just prior to the webinar around availability of fiber in slickline and cables, and also the ability to create or have a wireline tool at the bottom of the fiber transmitting back to surface. It's fair to say that slickline fiber is becoming increasingly available. It's also fair to say that we do have the ability to embed fiber within braided cables and have copper conductors within them. So it's not unreasonable to request your service provider to have fiber within cable, so that it gives you the option of running a fiber survey if needed.
Yeah, I think okay, there's a a question here. Is there also application for entire field management utilizing fiber? Yeah, in this case, we were really kind of in this webinar trying to highlight, how the data can be used, particularly around intervention type of surveillance that would be typical for slickline and E-line use. So I think Mike has pointed out that there is, there is certainly well stock out there that has permanent fiber installed, and certainly those type of wells, offshore high value wells, maybe a number of wells on the platform have the fiber installed, and that data is continued streamed back and used to do continuous monitoring. So definitely that's one of the applications. I think I mean, Mike, you can go ahead and comment on that.
So the question about using this field wide is an interesting one, because all the examples and all the things that we've shown so far are single well. This well has a problem, what do I do with it? It is fair to say that there have been studies out there using monitor wells and target wells where we make a change in one well and observe it in another, and that's typically I know in my former company we did that in the lower 48 with some fracking for unconventionals, but more recently in some of the North Sea type applications where you have a well pad or a platform where you've got the convergence of wells underneath a particular facility, it's very common that the individual well will react to things that are going on in the overburden in the offset wells. So the ability to run short, sharp surveys within a well or a series of wells is actually a really powerful one. And this might not necessarily involve permanent fiber. Not everybody can afford, not every well can afford the luxury of having permanent fiber in place. But the ability to run a slickline or fiber optic dart surveys in quick succession over a number of different wells and use that data in tandem to come up with a more holistic solution to the problems in the overburden is actually quite a doable one. So we do kind of ignore, we tend to think of wells as individual entities, but as they converge in the overburden to underneath a template or a manifold or a platform, then they are actually quite close together. And so any issues in the well because of leaks or porous and permeable beds that are starting to cause issues in one well can rapidly expand out into other wells, offset wells. So yeah, I have seen examples of that. That is quite a common thing.
Okay, thanks, Mike, on that. And yeah, I mean, I think again, just going back to the the focus of today, talking about contrasting fiber with wireline. I mean, we tended to focus around single well in the same way that slickline or E-line surveys are made. So that's kind of explains it. There's another question here from a gentleman asking about how sensitive is the acoustic reading? Is it option to use as a receiver for microseismic applications in an offset well for fracking?
Yeah, it is, and for those type of applications, then you would tend to need quite a high-end system, so a high-end surface interrogation unit and higher-end processing once you've acquired the data. So it's no different to if you were running a seismic survey, then there's a fair chunk of processing required to extract the best out of that. but increasingly we're seeing fibre being used as a replacement for traditional or conventional VSP surveys. And there are service providers out there that specialize in these high-end type services. The sort of the side of the business I'm in, I've always worked mature fields and old production wells, so I tend to get excited about flow assurance, well integrity type issues. I've never been a particular, it's never really been a passion for me to look at the seismic end of the spectrum. Thankfully, there are people that do that sort of thing, and there are companies out there that will provide an excellent service in terms of seismic quality acquisition from distributed acoustic data.
Yeah, thanks, Mike. I think just to add to that, there are some, I would say, specialty what's being promoted as engineering fibers. So, the typical fiber optic cable obviously comes out of the telecom industry, and on the telecom industry, they're trying to get light from one end to the other. So the best quality fiber is the one that has the purest quality. But in a distributed fiber sensing applications, we're not worried about what goes through the fiber. We're much more interested in the backscatter throughout the length of the fiber. That's how the measurement's made. And so actually fibers with more cells or more points for this refraction and reflections to occur actually increases the SNR increases sensitivity, especially for these microseismic applications. So you're right, it requires these kind of high-end boxes. It also requires good, relatively good coupling between the fiber and the well bore, whether it's the casing or the formation. So there are some challenges, but in this what I call the near well bore applications of flow assurance, then the sensitivity is not as much of a concern. So I don't see any further questions here. I just wanted to mention that yes, the fibers themselves are often packaged into a slick line type of cable. So in the center of the cable there is multiple fibers. So they are becoming more readily available. And I think the challenge here is to educate right across the industry on the value of these measurements, because one of the challenges I think we see is that the operators or the service companies tend to follow what the operators require, and so if they're not in the tenders, then it's something that they're not interested to provide. I mean, I'm talking about within the cased-hole surveillance. But what we are seeing, and what I'm seeing here in the Middle East, is more wireline, slickline contracts coming out that have fiber as a surveillance as a component of them. And so as these requests and requirements come out, then it's going to become more ubiquitous. So there's a question here. It says, would it be safe to say that the main source of DAS DTS data acquisition will be from the slickline, wireline, or similar deployed service for permanent monitoring?
I think the high value wells will probably end up having fiber permanently installed in them. So for example, if you had a well that could stand the expense of running a pressure temperature gauge, then why not stick a fibre in that gauge cable as well? Whether it's an optical gauge or an electrical gauge, it doesn't really matter. But the fact that if it's a high value well and you've gone to the expense of sticking pressure temperature there, then why not include fibre along with that? It gets quite tricky putting fibre across the sand face because of the issues with wet connects. They are improving, but they're not perfect, and so there is always a risk in terms of getting fibre across the sand face if it's a multi-trip completion. And then likewise, there's always the hydraulic conduit way of deploying the fibre, where you've got a turnaround sub and a 1/4-inch control line going all the way down, that you can blow the fibre down and back up again. So it's a double-ended system. So those are in existence and have been used quite successfully. But that's quite an expense, both in terms of rig time and capital to install that stuff. And if we want to bring this to the mass market, then I feel that slickline is absolutely the way to go, because every rig on the planet has a slickline capability. If you could use your conventional slickline crews and pressure control equipment and have a drum of slickline enabled fibre that is just dropped into the winch unit for you to make a survey, and then that can be used time after time after time in many different wells. It spreads the cost of the fibre enabled slickline over many wells over many years, and all of a sudden it starts to become a much more economic service. So I personally think that the cheap, easy, simple ways of deploying fibre in wells will start to open it up to a much, much wider well population, and it will really take off. And hence why I'm personally quite keen on the slickline and fibre optic dart type deployment methods.
Yeah, thanks. Yeah, I would say, I mean, what I usually say to people is that, the permanent monitoring systems, are probably in less than 0.1% of the world's well stock. I mean, that's probably a way overestimate. So 99.9% of wells have no permanent monitoring system, but most of those wells will have some type of intervention done, slickline, wireline, on a fairly regular basis. So I would say today, there isn't a lot of slickline, wireline work being done with fibre, but then that's that means there's an opportunity there. So for the future. So, are the slickline, wireline providers globally are the main source of this data today? I would say no, but tomorrow we're hoping yes.
And the way to think about it is this: most companies wouldn't think too hard about running a slickline memory pressure survey in a well periodically to monitor reservoir pressure, or whatever you're using your pressure for. It was a very common activity to on slickline have a pressure gauge run periodically in a well. Why wouldn't that be a fibre enabled pressure gauge? So you would have a distributed survey with acoustics and temperature, as well as your conventional pressure gauge. That's a really powerful surveillance combination. And so you're already going into the well to take a pressure. Well, why not use exactly the same kit, other than swapping out the drum for fibre enabled drum, to give you a much richer data set. So I think that would be a really powerful combination to gather that suite of information periodically in the well stock.
Okay, thanks. Yeah, there's another question here. Are there any comparisons between a cement cure DTS and CBL results? We didn't show one. I know that I've seen some around, but again, I don't see a lot of that being done.
Yeah, now that's an interesting one, because certainly one of the early cement logs, for want of a better word, used to be running a temperature log in a well, and we're going back, many decades, where temperature, the exothermic reaction was what we were picking up on. Now, cement data is, well, there are certain regulatory authorities that insist you have to have some sort of indications of where the cement is. And as long as you can get the fibre in the well when that exothermic reaction is occurring, then it's a perfectly acceptable way of monitoring where there is cement and where that reaction is taking place. However, like all cement data, it's no guarantee of hydraulic isolation. It may tell you the presence of curing cement, but it certainly doesn't tell you anything about the quality of the cement, nor about the bonding or any channels, or there's many other things. But if all that's required is the presence of cement and the curing process is active, then temperature is okay. And again, for cementing purposes, my personal preference, I kind of like the cement mapping tools, where you get some sort of circumferential view of cement, so I know, yes, it's there, and there are no obvious channels in it, and it's bonded to at least the casing, if not the formation itself. So I'm always a little bit cautious when we talk about cement, and that includes cement logs, because they're great for telling me about the presence and quality of cement, but nothing about hydraulic isolation.
Okay, thanks. Another question here was, what are the absolute accuracies of temperature in the DTS measurements?
Yeah, that's a really good one, because I like using distributed temperature as a good relative measurement tool. If I looked from trace to trace to trace, then there would be variations within that temperature, but I would always want to run a memory or a surface readout pressure temperature gauge at the bottom of my fibre anyway, and that helps me normalize any perturbations in the distributed temperature survey and correct those for any anomalies. These are sensitive instruments, these interrogation units, and they are subject to change if we have too much surface activity going on. And by that I mean they're sat in a shack and somebody opens up the door and you get a blast of cold air or hot air, depending on which part of the globe you're in, that chills down the reference coil or the instrument itself. And so I like the ability to have a temperature reference, a good absolute temperature reference at the bottom of my fibre used to correct that temperature too. However, the actual DTS data itself is a good relative temperature measurement, and so we can. And this is another way of playing off the strengths and weaknesses of distributed versus wireline. So wireline, that's where I'd be pointing to for my good point absolute temperature, but then the DTS is what's giving me a relative change over that survey interval. Sorry, that was stunned silence. Did I answer that one?
Sorry,
Okay, Marvin.
I'm talking with the mute on that's why I'm talking with the mute on, sorry. There's another question here, which was deploying fiber slick line in horizontal wells. I mean, is it possible to deploy horizontal wells?
Yeah. So slickline and darts are great if you want to allow gravity to do the work for you, but despite having as many of these your fancy rollers and various other things to help you get down, it can only go so far. So having a means of pushing that fibre down, GOWell have got a perfectly good carbon fibre rod that has been used to deploy fibre in horizontal sections, and you've always got the ability to drag it down there by tractor. And so there are many tractor providers on the market, and there's more coming on the market as we speak, where we can drag the actual cable or the slick line down to the bottom of the well. Some of them are powered, some of them are battery operated. So the options for getting your fibre to where you want it to in a horizontal well, those are increasing, and we do have the ability to do that. We've also got, sorry, I keep forgetting about coil. If you had access to coil, then you could have fibre enabled coil where you could push that down to the bottom of a well also. I tend to, that's quite big kit, and so I quite like small, light, nimble, portable stuff with small crews, which is again why I kind of look towards the slickline end of the spectrum rather than the coil end of the spectrum.
Okay, thanks, Mike. We've hit the hour, which was our target for today. Much appreciate everyone joining in today. All the questions were good. There will be a recording of this webinar that will get posted up shortly. Again, if you have any questions, then you can certainly email us. You can just reply to the reminder that went out yesterday. Please keep a lookout for our next in series for these webinars. If anyone has some suggestions on kind of subject matter, right now our next webinar is going to be focusing around one particular case study from end to end, how the data is acquired, how the data is analyzed, and how to make sense of that particular data set. So more, let's say, more granular detail than we went over today. Okay, well, thanks again for joining, and this is the end of the webinar, and appreciate everyone's attention. Thanks, Mike.
Great. Thanks. Bye.
Bye.